Hi, everything is fine. And I would like to say welcome, everybody. It is our privilege to have somebody very, very distinguished as a guest lecturer. This is Professor Roberto Navigli. I have had the pleasure of knowing him for more than 15 years. We met at ACL in Athens in 2009, I think. And I could see him as the most successful computational linguist in Europe ever since. And he has been showing this every day. He has top publication after top publication, award after award. He has, so many special awards. He's triple AI fellow, aren't you, Roberto?
That's the most recent one.
Yes, the most recent one. He has several ERC projects, and one of them has been defined to transform the research in Europe. I mean, he's really amazing. If I keep on talking about him, it will take the whole time. So, thank you for joining, Roberto. Thank you for being with us, with the students in Lancaster. So, I'm going to give you the floor. We have about 45-minute presentation followed by 10 minutes of questions. Thank you very much.
Thanks a lot for this great introduction, Ruslan, and thanks for this invitation. So I'm really happy to give this talk, because actually this is a talk that summarizes probably more than 15 years of research. So I'm trying to wrap up a number of research works that are all interconnected, including very, very recent work presented last year at ACL, and in a sense continuing the tradition of lexical semantics and sentence level semantics in a world where everything is governed by deep learning and the transformer. So the title of the talk is What's Behind Text, the Long Challenging Path Towards a Unified Language Independent Representation of Meaning. Most of this work was carried out by students, PhD students, postdocs, and researchers, together with me at the Sapienza NLP group, in the Sapienza NLP group of the Sapienza University of Rome. And you see here the names of most of the contributors. Unfortunately, there's no time to read them all, but you can take note if you're interested. During the slides, I will also mention their names. So the starting point is that actually LLMs are very different from the way humans speak, talk, and reason. And so if we think about that, the fact that LLMs need trillions of tokens to be trained, a good reader can read 200,000 words per week, which means in a lifetime less than 1 billion words. And so we don't need to wait until we're old to start talking. So that's a big difference already. But also the fact that LLMs don't talk about things they have experienced, while we connect language to our word experience. And there's quite an active debate about whether we are creating very powerful stochastic parrots. So the main question is, what are we really, what are these systems really understanding? And so while we all know that with the advent of ChatGPT, large language models have really proven their usefulness and their impact, all that glitters is not gold. If we take this example, and we can find many others, Prof. shot, word shaken. This happened in the 80s. And we all know, those who were there and those who read about it, all know what happened. He was shot. Well, then if we translate into Italian, we get actually from a state-of-the-art LLM system that it's not that he was shot, but that he shot. So Papa Wojtyla ha sparato, il mondo è stosso, the world is shaken. But now the question is, and we even have a proof of this through a fake image generated with Flux. Of course, this didn't happen. It never happened. And it's very unlikely to happen. So the question is, why did an LLM produce such a sequence of tokens? Because it didn't understand, first, that it's unlikely to happen. Second, that common sense, it's much more likely that the Pope is exposed to the possibility of being shot than the action of shooting. And so these two things together give us an idea of the issues that we are facing. And more examples are translating to Italian. An example is the best agency of instruction, for example, here. And I'm trying to use my pen, but it doesn't seem to work. Okay, it doesn't matter. Translate into Italian, an example is the best agency of instruction. And we get a very funny example here where agency is translated into agenzia, which is the main predominant meaning of agency. But it doesn't make sense in this context, because here agency means way. And so probably the best example is, the best translation is miglior mezzo in Italian. But for example, Gemini 2.0 provides 3 possible translations. One is a bit of a stretch, maestro. One is incorrect, il miglior agente di insegnamento doesn't make any sense. And one is correct, but it cannot really choose between these 3, right? And many other examples can be found. Like here you see a lot of mistakes made in different languages by state-of-the-art large language models aimed at translating, like here GPT 3.5, GPT 4.0, etc. And actually, in a study that we are about to publish in the Computational Linguistics Journal, and that we presented the first time at ACL 2022, we created a benchmark for evaluating the ability of machine translation systems to identify the most appropriate translation for an ambiguous word in context, given that that word is used in a non-predominant meaning. So if we say he poured a shot of whiskey, shot has multiple meanings, and in this context, in this meaning, this is not the predominant meaning, according to certain corpus. And the question is, what are the good translations of shot in the different languages? For example, bicchierino, goccio in Italian, while bad translations are shot in the meaning of shooting, like sparo, or in other meanings, like iniezione. And what we did was to manually curate such a data set in many, many languages, and then see how good were the different state-of-the-art machine translation systems at choosing the most appropriate translation for the ambiguous word. And so this is the DPMT system for disambiguation bias in machine translation. And the data set covers very many different domains. You can see from philosophy to business, textile, music, all kinds of domains. And these are actually the BabelNet domains. BabelNet is a large knowledge graph, multilingual knowledge graph that we created in my group. And you can see here the results. That's interesting, because even the best possible translation systems, and among these we can count GPT-4 and DeepL, struggle to translate these ambiguous words used in non-predominant meanings across languages, with some languages being harder to translate appropriately, like, for example, Dutch and Chinese for some systems are harder. But you can see that even the best possible system in Dutch, for example, in German, for example, DeepL, gets right a bit more than 3/4 of the instances in the data set. And so this means that actually a big issue, while machine translation is doing better and better, there's still the issue that these systems don't really understand the meaning of words in context, especially when we use them in meanings that have been seen not so often in the training corpus. And this is the motivation for all this talk, for all the work that I'm presenting here today. We started almost 20 years ago with what I call the semantic roadmap. So we have resources to start with, because in order to be semantic, we want to explicitly ground the meaning of words, but also of sentences, to existing knowledge bases or multilingual knowledge graphs. And here I'll talk briefly about BabelNet, VerbAtlas, noun atlas, and also the bubble and meaning representation. Then we need systems that take words in context, and so carry out the word sense disambiguation task, but also that consider a whole sentence and identify, detect, and produce the semantics at the sentence level. And so this is semantic role labeling and semantic parsing. And finally, we need data sets, because these are, in today's NLP supervised systems, we need data sets that help first make this data openly available, and second, to enable to train supervised systems with high quality annotations. And finally, we would like ideally to show usefulness of this semantic approach. So let me start with the tasks. So basically, I'll tell this story going task by task, starting with word sense disambiguation. So this is the word level semantic area. So word sense disambiguation, what is WSD? The WSD is a task of assigning the most suitable sense to a given word that appears in context. For example, the traditional sentence, the quick brown fox jumps over the lazy dog, we focus on the word fox. And we have a listing of the possible meanings from an existing resource, a dictionary, a knowledge graph, like, for example, WordNet, and we would like the system, the word sense disambiguation system, to choose the most suitable meaning for this word in context. And in this case, it's the first meaning of fox, the mammal. Now, there are three limits here. First, that there were three limits, actually. So that when we started doing our research, the focus was on English, because the inventory for the meanings of a given word, any dictionary word, was on English. And so WordNet was the predominant resource. It's a freely available computational lexicon of English. However, WordNet not only is focused only on English, but it also has little coverage of entities and specialized knowledge. And it also comes with a very fine-grained set of sense distinctions. We are not going to cover this third point because of lack of time, but this is also another point to take into account, and for which we actually did a lot of research. But starting with the English limitation dating back to 15 years ago now, and little coverage of entities and specialized knowledge, what we did was to come up with a novel resource called BabelNet that we put forward already in 2010, and then we continued over time until today. So it means that it's 15 years that we've been updating this resource, and I'm very proud and grateful that we are still able to do that. And so what is BabelNet? It's a merger of many different lexical semantic knowledge resources. So the initial idea was to take WordNet as a lexical semantic knowledge graph, and bring it together with Wikipedia, which is the largest crowdsourced encyclopedia available online. So bringing together these two resources, and then later other resources like Wiktionary, Wikidata, and many other resources, either of a lexicographic or an encyclopedic type, actually provides several advantages. As you can see from this picture, if you take Wikipedia pages, we know that in many cases, Wikipedia pages starting from English are interlinked to their counterparts in other languages. Like here I have Italian, French, Italian, Chinese, and many other languages. And you also have the knowledge base of Wikipedia, which is Wikidata, a more recent project, still very effective and very rich in content. And so each Wikipedia page tends to be associated with a Wikidata entry, which provides a lot of information in structured form. And so then what we do is to link Wikipedia pages, starting from the English pages, to the most suitable sense in WordNet, which is a dictionary. And at the same time, later, we also linked WordNet to Wiktionary and other resources. And as a result, we created, in a sense, an alignment between entries in different resources. And as a result of this alignment, what we could do was to start from the WordNet synset model, where a synset is a set of synonyms that are used to express a given concept. Like, for example, if we want to express the concept of car, the synset corresponding to it, it contains the words, the synonyms car, motor car, auto, automobile, and others. But then, thanks to linking this synset to the English counterpart, the English page in Wikipedia, we also link to automatically, thanks to interlanguage links, to other languages. And so we know how to translate this synset into other languages, and we can do the same also using Wiktionary, Wikidata, etc. So as a result of this, we create a multilingual synset that now contains translations and lexicalizations in as many languages as possible, up to 600 languages. For example, in Italian we have autovettura, macchina, autoveicolo, and voiture in French, etc., etc. And we also collect all the edges that connect the nodes of the different resources that we integrate. As a result, we obtain a multilingual knowledge graph that brings together concepts, like, for example, here, circuit board or central processing unit, to named entities like Commodore International here, Commodore 128, VIC-20, etc., etc. Not only that, but because we keep updating the resource, the number of languages grows because we integrate more and more resources. These resources grow over time, and now we have almost 23 million synsets covering more than 7 million concepts and more than 15 million named entities. And all of this in so many languages that this could certainly be the starting point to address low resource languages in many of the directions that today worry us. Now, how do we use such a resource to carry out the word sentence ambiguation task? For example, here you have, again, the very same sentence: the quick brown fox jumps over the lazy dog, and its Italian translation, la veloce volpe marrone salta sopra il cane pigro. And what we can do now is, if we have a system that can associate the most relevant meaning with each of these words, actually, as you can see from this example, the synset that is associated with the English words ideally should be the same as the synset associated with the Italian words in context. So this means that brown and marrone are associated the same BabelNet synset, analogously for fox and volpe, for quick and veloce. And you can see that sometimes these synsets are not in the same position because in different languages words follow a different order, but the synsets ideally should be the same. I'm saying ideally because this is an example and it actually works. But in other examples, maybe you have a synset that is related but is not exactly the same. Still, it's a very interesting way to, in a sense, ground the meaning of words in context. Now, over time, how did we carry out the word sentence ambiguation task? Well, I'll start from 2014, when we introduced the Babelfi algorithm, which had the great innovation of bringing together the word sentence ambiguation task and the entity linking task, because we were using BabelNet, and BabelNet, as I said, brings together concepts and named entities, and as a result of this, we can use the same algorithm, which at the time was a graph-based algorithm, pre-neural era of NLP, still available, so you can still use it online, babelfi.org, and with the big advantage of being able, thanks to the graph algorithm and the graph being language independent, to disambiguate in arbitrary languages. So this was way before we're talking about multilingual LLMs or transfer learning, etc., etc. So very interesting. More recently, we started to use the transformer to carry out the word sentence ambiguation task, and we introduced the WordNet adjacency matrix into a transformer-based architecture on the encoder side. Here we were using BERT in order to exploit the connections in WordNet and bring and provide more strength to the choices made at the softmax layer by bringing together the logits of synthets that are interconnected through a relationship. And we called these logits structured logits because of this. This was ACL 2020. Then more recently, we thought we would like to work with an open inventory, because this system here is trained with data that is annotated with WordNet. And so you can still scale to other languages thanks to BabbleNet, but you're bound to the inventory that is provided by WordNet. But now, with this approach that we presented at NACL and later at EMLP 2021, we exploited the BERTA, but we could have used also BERT, to input not only the sentence and its target word, but also, after a separation token, the list of textual definitions for the word we're interested in, that can come potentially from any dictionary. So of course, I'm still going to train the system with WordNet annotated data, but later I can test it at inference time with new inventories, as we did. For example, we used the Oxford Dictionary of English. And this is very interesting because it gives a lot of freedom in terms of choosing the inventory of interest. And recently, we presented this at ACL last year, 2024. We also wanted to fill a gap in the literature, because word sentence disambiguation has always been carried out by assuming that we know the candidates. We know which word we have to disambiguate, and we even know it's part of speech. While in the real world, in the wild, we just have a string, we just have a text, a sentence, and we don't know exactly which span we want to annotate. And so we introduced a novel, surprisingly a novel task called word sentence linking, where we don't only perform the disambiguation task, but we also perform the candidate identification task, where we identify the spans that we then need to disambiguate. And we did that with a retriever-reader approach. And the good advantage here is that we don't need to pre-establish the candidates. We don't need to know what to send tag. And one of the most recent systems that we released doing state-of-the-art word sentence disambiguation is Amuse, that you can use or download or use online. And now, if we disambiguate, an example is the best agency of instruction. Maybe we're lucky, but we get the right disambiguation of the word agency, which means that if I push a button, I view this inset in Italian, I don't get agenzia as a translation, but most likely mezzo or another synonym. And now moving to the sentence level, because this is all to say, okay, I have a system that takes a word in context, that disambiguates this word. Now, why should I do that? Well, there are many reasons to do that. Of course, today with large language models, people are seem to be interested only in generating other text starting from text. But there are many reasons why one would like to ground the meaning of a word, and now we'll see the meaning of a sentence, to an existing resource, to an existing entry that a company has an interest in considering, and that can be leveraged to enable semantic search or an analysis of what comes out of the disambiguation system, etc., etc. So now moving on to the sentence level, the first task that comes to mind is semantic role labeling. Again, let's consider the same sentence: the quick brown fox jumps over the lazy dog. And here, what we do with SRL is to identify the predicate argument structures, meaning that those verbs, but also those nouns and potentially adjectives that denote, that have the function of being predicates, have to be identified. And so here, jump is the predicate. And what is the meaning of jump here? We perform a similar task to that of word sentence disambiguation that we call predicate disambiguation. So given that we have identified a predicate, we disambiguate it. And we disambiguate it using an inventory that surprisingly is different from WordNet. So because these two tasks have been historically were historically proposed at different times with different backgrounds, a new inventory was created starting from theories like frame semantics, basically. So now that we have disambiguated the predicates, we can identify the arguments of the predicates, because now that we know what is the meaning of jump as a predicate, now we can say these are the spans that in a sense, represent and contain the arguments for this predicate. And finally, what we have to do is to disambiguate these arguments. So, for example, who is an argument, or arg0 is the argument, and over what is another argument that we might call arg2. Now, what is the meaning of arg0, arg2? Well, I'll come to it very soon in a second. Now, the three main limits of semantic role labeling were, before we started doing research in this direction, were the English focus, again, because many many tasks in NLP have suffered for a long time for being focused on English only. And then the focus on verb predicates only. So the historical resource here is PropBank, used in semantic role labeling for a long time, and mainly focused on verbs. Still, there is NumBank, we have to say, but NumBank was then at some point discontinued, and now PropBank also includes some nominal information, but it's limited and it's not a first-class citizen. And finally, there's no connection with the lexical semantic level. So I would have liked to see, I don't know, this jump 03 to be connected to a BabelNet synset, or to at least a WordNet synset, which is not the case. And so starting from the literature, from the resources, the most popular resources, FrameNet, VerbNet, and PropBank, we realized that each of these resources suffer from different issues. And so, for example, FrameNet and VerbNet have incomplete coverage, so they don't cover all the possible predicates that you can express with verbs, for example. Or PropBank and FrameNet have predicate-specific roles, like, for example, arg0, the arg0 I showed earlier, or arg2, have a meaning that depends on the predicate. So if I change the predicate, the meaning of arg0 might be different. Or they, in a sense, miss the semantics of verb classes. Like, for example, there's no notion of a class, of a semantic class that can cluster together predicates and transfer knowledge across predicates that still, in a sense, clustered together. And finally, as I said, all these resources are tied to a specific language, mostly English. And so the idea that we had in 2019 was to start with WordNet, actually, and consider all the verbal synsets in that resource, and bring together all those synsets, all those verbal synsets that have similar scenes and participants to the action. For example, we created the eat byte frame by clustering all those synsets that express the verbal meaning of eating in different ways, like munching, dining, ingesting, eating, and also biting, swallowing, etc. And analogously, we created another frame, for example, the one of cooking, with all the ways of cooking. And this was done by a linguist who was interested in creating a computational resource that was manually curated, grounded on principles, on linguistic principles, but also on the usefulness of clustering and connecting to WordNet. And as a result of connecting to WordNet, also of connecting to BabelNet, because each BabelNet synset that contains a WordNet synset can be then extended multilingually by just considering all the lexicalizations that I showed, for example, in a previous slide. So once we have linked, once we have clustered synsets in WordNet, each of these synsets is one-to-one with the BabelNet synset, and which is a superset of the lexicalizations that are found as synonyms in a WordNet synset, and that contains all the other lexicalizations in the other languages. So by doing this effort, I'm creating frames that are multilingual by design, even though I start with English in the clustering process. And then we had another idea, and this was presented in ACL 2024 last year, and even got the Outstanding Paper Award at the conference. So how to scale from verbs to nouns? So we didn't want to the work done with this resource that we called Verb Atlas, by clustering all the verbal synsets. We are talking about more than 13,000 synsets in WordNet into more than 400 frames, so much coarser grained frames. First, this guaranteed wide coverage because we covered all the possible verbal predicates. But now the question was, how do we scale to nominal predicates? Like, for example, eating, lunch, or theft. So all these nouns express a process, an act. And so they can still be used as predicates. And they can also have arguments. And they can even use the same frames because the bite as a noun, or the eating, or the lunch. So these are all synsets that should fall into the same frame, eat, bite. And so the question was, how do I extend this to nominal synsets that express a process or an act, etc., without having to do this manually? Because here we are again talking about tens of thousands of synsets. So what we did was to identify the corresponding nominal synsets to the verbal synsets in WordNet. And this is easy because WordNet comes with relations that connect such pairs of synsets, like the nominalization of a verbal synset is found in WordNet. Now, this was easy. So we just added more synsets. And then what we did was we clustered together those synsets, those nominal synsets that, in a sense, express analogous semantics in nominal form. This is not so obvious because it's not always the case that the nominal synsets are interlinked to the verbal synsets. And so we applied a number of strategies to bring together, to identify the appropriate frame for each nominal synset that expresses a process or an act. And as a result of this, we created Noun Atlas. So this nominal part is called Noun Atlas, and the whole resource is now called Frame Atlas. So this means that now we have verbal predicates, nominal predicates, and these are all clustered together into one frame. And this frame is now part of speech independent, language independent, because these synsets are in BabelNet. And so the fact that we started with English doesn't mean we cannot do this in Italian, in Bulgarian, in Romanian, or in any other language we're interested in. And interestingly, we also paired the semantic role set with each frame, starting from VerbNet. So we chose to use a set of semantic roles so that are independent of the frame. And the best possible solution came from VerbNet because they used they were inspired by the historical thematic roles like agent, patient, instrument, and result and location and other roles. So this means that now we have human interpretable argument labels. And so agent, patient, these are much more readable than arg0 and arg1, also because, as I said, these relation labels are predicate specific, while these ones are actually cross-frame. So the meaning of agent is independent of the frame. It's an agent, so it has a semantics that then can be, of course, specialized for a given frame, but that is frame independent. And so how did we perform? How do we perform the semantic role labeling task? In 2020 and more recently in 2024, in the ACL paper, we used a multilingual SRL encoder-based system that starts from an input sentence, provides the word representations, and then creates predicate-aware representations, and then performs the first two tasks that I talked about, predicate identification, predicate disambiguation, and then informs a second part of the neural model that produces predicate-specific argument representations that are then used to perform the other two tasks of argument identification and argument classification. And in 2021, in a NACL paper, we went on by creating a universal encoder. So we had the idea to have one output head for each resource. So in English, we have prop bank, as I said, and most data is annotated with prop bank predicates, which are independent of WordNet, independent of other resources, the Chinese prop bank, the Spanish and Catalan Ancora, and then even Verbatlas, which is, as I said, language independent. And so we trained this model to encode the sentence in a universal way by, in a sense, using the loss during training that corresponds to the input sentence. So if I give as input a sentence in Spanish, then I value, of course, I have only knowledge about what is the correct predicate meaning in Spanish. Still, the fact that then I also input later in the same batch data that is annotated with another resource means that the encoder, the sentence encoder, tends to provide a representation that has to scale across languages and across resources. And so as a result of this, the system, in a sense, learns to pair the different labels from the different resources and allowing, in a sense, to align these resources across languages. And then we take this sentence encoding and we give it as input to a universal predicate argument encoder, which then outputs the most relevant role for a given token. And it does so again with the head for each and every resource, so that the model learns, once I give as input a sentence, to annotate each predicate and each, for example, through here, or through here with the various predicates in the different resources, and in a sense allows us to align these predicates across resources and across languages, and the same for the different role labels associated with different words. And interestingly, because we're using a multilingual model, once we have trained in 6 or 7 resources, then we can use a new language that was not seen at training time, like Italian, which doesn't have annotations for semantic role labeling, and still the model is able to output the most relevant predicate sentences and corresponding labels for the different arguments in all the resources. And now that we have Verbatlas, we can use a language independent frame associated with for example, an Italian verb, and the corresponding labels for the arguments. This is an existing system that can be downloaded or used that implements this task in Vero XL. And if you try it out, for example, here I tried in English, the mouse ate the cheese that I bought at the supermarket yesterday. 2 predicates are identified, eat, bite, and buy, and the corresponding role spans are identified and labeled with VerbNet inspired frame independent labels. The third task is semantic parsing. So in semantic parsing, actually, we move to a level where we not only identify a predicate and its arguments, but we transform the whole sentence into a graph. For example, jump 03, which was our predicate in the standard sentence, the quick brown fox jumps over the lazy dog, is identified as a node, and then its arguments are connected through directed edges. And so, for example, fox and over. But then, rather than having a whole span, we further structure the span. For example, fox has 2 modifiers, brown and quick, and here actually we are using brown and quick as predicates, and so in a sense fox is the argument of brown as a predicate and quick as a predicate. And the interesting thing is that this graph potentially can be produced for each and every language. For example, if I translate this English sentence into Spanish and Italian with different words and different orders of the words, ideally I would like to produce the very same graph. However, please note that this graph on the right-hand side is in English. So this means that before the work that I'm going to present, actually the semantic parsing task, because of, again, focus on English and the fact that the most popular representation called AMR for abstract meaning representation, and all the nodes being in English, and all the nodes representing words actually. So if you see here, dog is an ambiguous word, fox is an ambiguous word. Some of the words are disambiguated, and they are disambiguated because they are predicates. And so all the other nodes are not concepts, they are just words. And so this means that if I want to perform AMR parsing in English, in Spanish, in Italian, or in Chinese, and I don't have enough training data for that language, the main thing I can do is to train it cross-lingually to produce an English AMR graph, which is a limit not only for the language, but also for the fact that these nodes are language specific and ambiguous actually. And so we came out with this idea of the bubble net meaning representation, BMR. So BMR aims to move from a graph where words are ambiguous and language specific to a graph where we replace these words and these predicates, these language specific predicates like coming from prop bank, with respectively BubbleNet synsets. So we replace fox with the BubbleNet meaning of fox in this context, same for dog, same for lazy, etc., and verb atlas or noun atlas frames that replace the prop bank frame sets. And interestingly, because this verb atlas or noun atlas frame is a clustering of verbal synsets or nominal synsets, this is still connected to BubbleNet at a coarser grained level, and potentially we could even disambiguate jump with BubbleNet, so we could even add a synset with the same granularity as BubbleNet. And so the idea here is to bring together, to go to the roots actually of AI, where the dream was to have a semantic representation for the input sentence. And so if we have sentences in different languages, we want, or the same, or paraphrased sentences in the same language, like these two sentences in English here, ideally we would like to produce the very same graph or a similar graph that doesn't use words, but uses concepts and semantic relations. Now, how do we do this truly semantic parsing? We had the idea of carrying out seek-to-seek parsing, thanks to the linearization of the AMR and then later BMR graph. And so what we did was to train a seek-to-seek model, like we started with BART, and later used more sophisticated approaches, to take as input a sentence, a sequence of tokens, and produce a linearized version of a graph. And we used three different ways of linearizing: Penman annotation, DFS, and BFS as different strategies to search the graph. And as a result of this, we create a sequence of tokens that represent the structured graph. And then we perform some post-processing. We decode this sequence into a graph, and we finally perform entity linking. This was presented at AAAI 2021 and is a very popular system called Spring that you can also use online. And then more recently, we transformed this into a fully semantic approach where rather than producing an AMR graph, which, as I said, is language specific, we produce a BMR graph where the nodes and the relations are language independent. As I said, this system is online, so you can try it out. Spring and then Unirova 1, because Spring is such an ambiguous word that you will not find it if you just query search Spring. Okay, now the question, the final part of the talk, and I still need another 3-4 minutes, Ruslan, is how is semantics doing? I mean, we never talked about performance. And here you see that word sense ambiguation, semantic relabel, and semantic parsing over time have been doing pretty well, following, in a sense, the success of neural approaches that have increased the performance of many tasks in NLP. And so when I was a PhD student, and basically we were here, the performance of word sense ambiguation was 64, 65. And now we are at 83, more or less on the same data. So it's much more interesting, of course. And we are using a very fine-grained sense inventory. Semantic role labeling and semantic parsing also followed a similar path. And you can see that the results as of 2024, 2025 are very, very interesting and start to be useful and usable. Still, there are a number of questions. How can we integrate these tasks? And so can we integrate the lexical and the sentence level tasks? So can we study the interplay between them? Can we reduce the dependency on closed data sets? Because some of the data that is used for training these systems is not available or is under a certain license, and go multilingual. And so to do so, to address these issues, we presented last year now called MOSAICo, a multilingual open text semantically and interlinked corpus that aims to interconnect all these tasks by providing large-scale training data that, in a sense, use as interconnected a resource as possible that, in a sense, brings together all these tasks. And we also added the task of relation extraction. So how does it work? We have a sentence, like, for example, my cat ate the mouse that I bought at the Apple store, blah, blah, blah. And then what we do is to perform the word sense disambiguation task with the state-of-the-art system. We do the same with semantic role labeling. We annotate the same sentence with the Invero SRL system. And then we perform semantic parsing with Spring. And finally, we also perform relation extraction with the Rebel system that I didn't have time to introduce. And so we annotate this sentence with a lot of different rich information that comes from different tasks that, interestingly, is interconnected across tasks. For example, if I disambiguate mouse with the right meaning, the right synset in WordNet and in BabelNet, this also is also connected with the meaning of the node in the semantic parse tree. But even more interestingly, predicates chosen at the word sense estimation level, like by as a verbal synset, must be contained in the corresponding frame that was selected by the semantic role labeling system, or by the semantic parsing system. And so we can study the interplay and even find mistakes by performing these tasks independently and seeing the idiosyncrasies across tasks. So how did we build this data? We started from Wikipedia in 5 languages, English, Italian, German, Spanish, and French, and now we're extending to more languages. We performed the selection of those articles that appear in all these 5 languages to guarantee the popularity of the topics. Then we process this text, sentence splitting, tokenization, lemmatization. We perform the 4 tasks automatically. And we also produce the higher quality version containing only good and featured articles in Wikipedia that are manually tagged with such labels, so that we have a smaller version, MOSAICo Core, which comes from higher quality resources, articles. And as a result of this, we increase the amount of data considerably in all these 4 tasks. So this is the starting point, is the gray bar, and here we start here, and you can see that we sometimes produce more than 10 times, 20 times the amount of data, and even more in other tasks. So it's not only quantity, but it's also the fact that we drop the requirement of closed license data, because this data that we annotate here comes from Wikipedia, so it's openly available. And we also cover a lot of out-of-domain instances, because we use all of Wikipedia across domains. And we also saw that if we use MOSAICo, for example, here MOSAICo Core, as a replacement of the gold data that is covered by different licenses, we even get better results in the various tasks. So, or more or less on par. So this means we can replace now the gold data with the MOSAICo Core data, which is open, and perform these tasks, and also find interconnections across tasks. And so this is the result that we recently presented, and now we are starting to study the interplay between pairs of tasks. In conclusion, I put the stress on working with language not only at the form level, because LLMs, yes, they kind of understand because they have to produce a latent representation, but they never make this representation explicit. So my point is, let's focus on meaning too, and let's integrate meanings across languages and make these systems language independent. producing structured representations that enable scalability, interpretability, generalization power, accountability, manipulability, and all of this addressing linguistic diversity. So this is essential. And so to conclude, I'll leave you with the question that I expect from you guys, and if you want to further discuss it, I'm available. So the point is that this work keeps the pace with neural approaches, right? Because most of the systems I presented are neural-based. Still, the question is, hasn't all that work been superseded by the great success of LLMs? Well, in a sense, the answer is no. I can already anticipate no. First, because I started this talk showing that state-of-the-art LLMs, GPT-4o, fail to prove that they can really disambiguate words, for example. And so explicit semantics can be used to see the problems that current LLMs have and validate their results. And also, when it comes to less resourced languages, those languages that don't have enough data, LLMs still have a problem. So they still struggle to produce high quality outputs. And finally, as I already mentioned earlier, we really need, in many cases, to ground text to explicit entries in a knowledge base, in a knowledge graph, etc., etc. So all of this is very useful. Maybe you have other suggestions about this. So now, keep calm and use LLMs cum grano salis. Thanks a lot.
Thank you very much, Roberto. Inspirational presentation, as you said, summarizing the highlights of your research over the last years. It's really great to have you here. I'm going to ask whether the students or my colleagues have any questions or any comments. While we're waiting for the questions, Roberto, can I ask you a question? If somebody hasn't been able to attend your talk, which is really a pity, could we put it could we put the recording on the research group channel, so the YouTube channel, so that somebody can see it again?
No problem.
Thank you very much. So while we're waiting for any comments or questions, I wanted to ask you, on your penultimate slide, we spoke about
this one?
Yes, the LLMs are not there. I have done several recent experiments on machine translation and large language models, and they really don't do very well on low resource languages. But my question is, to what extent can we comment in terms of processing language which is not literal? We're talking about figurative language, we're talking about metaphors, we're talking about even multi-word expressions. So how would you comment on the performance of LLM towards other classical approaches when it has to do with non-literal meaning?
Yeah, that's very interesting. We have actually ongoing work on this that I cannot disclose, at least here in a recorded lecture, but we have some published work recently on figurative language, where we try to identify metaphorical use of language. And I think here there are two main levels. One is the identification, and one is carrying out the task. So I think that it's very clear that semantics helps at least screen and identify potential issues. And we showed that with the lexical translation bias in DBMT, but also with the use of figurative language, you can classify, you can identify that kind of use. And then if you see that the translation or the interpretation is literal, you raise a flag, and you know that something has gone wrong. So in this respect, I think these systems are very, very, very useful and powerful. Then in terms of whether they can help an LLM or another more traditional system improve the task, unfortunately, I think that if you don't know how to rephrase or the semantics, the explicit semantics of, for example, an idiomatic use of language, it's very hard, both for an LLM and a more traditional semantic system, to come up with the true meaning. And this actually holds also for humans, because if I don't know what red herring is, it's hard for me to translate this into Italian. So by this, however, at the same time, it's true that nowadays lexical semantic resources are very rich. And so most of these uses are covered. Maybe they are much more crispy and, in a sense, static than what we can generate or interpret with LLMs. But I think that the interplay, the intersection between these two technologies can really play a role here. So that's the idea. And we are working in this direction in a couple of different ways. And yeah, let's talk about it in a few months. And I think I'll be able to say much more about it.
Well, knowing your history, your track records, I know that if there is a breakthrough, it will come from you.
I hope so, but of course, many other colleagues are also doing very well, of course.
Roberto, you spoke about performance in word sentence ambiguation. Obviously, there was this paper from Jarowski many years ago, which was claiming very high performance, but then the evaluation was done only on a few words. And you just made a comment that now word sentence disambiguation has improved in terms of performance. What is the limit of semantic role labeling? How far can we go?
Yeah, so semantic role labeling has, in a sense, when I started doing SRL, I was surprised by the high performance of the predicate disambiguation task. So choosing the meaning of a predicate was above 90%. And I said, hello, I mean, in word sentence disambiguation, this is very difficult because verbs are very ambiguous and there are many meanings. Actually, it's interesting that in SRL, the granularity of the meanings is very, very coarse-grained. For example, in prop bank, you have seldom more than 2 or 3 different meanings for a given verbal predicate. And so in a sense, we mitigated this with Verbatlas, because in Verbatlas, you have a coarse-grained representation because you have these frames as clusters of scene sets, but it's somewhat in between, in a sense, more semantically principled. And so sometimes for a given verb, you have 7 or 10 different frames, which is much better than WordNet, though, because in WordNet, in many cases, you have 20, 30 different sentences. And so I think that semantic role labeling is one of the most interesting tasks here, because it enables the tasks of, for example, event extraction, event reconnection. For example, we are working on narrative understanding, and if you have a big book, yes, you can have a transformer that has a very long input context length, but at the same time, the question is what interconnects to what. And if you have predicates for connecting characters and locations, etc., across a long book, you can really not only study, but also view this information in a more usable form. So I think SRL is probably the most interesting task among these 3, I have to say.
Thank you very much, Roberto. I would like to thank you very much for accepting the invitation to give a talk to our Lancaster students who study natural language processing. I mean,
thanks for the invitation.
Having you a guest lecture is really a dream opportunity. Thank you very much, Roberto. We'll stay in touch and we shall see each other soon.
Thanks a lot. Let's talk soon.
Thank you. Bye-bye.
Ciao. Bye-bye.
Ciao, ciao.